The topic that we're going to be talking about today, artificial intelligence, is typically associated with robotics, with machine learning. We're trying to endow with intelligent behavior machines and other objects that we normally do not associate with decision-making or choice-making or intelligent behavior in general. However, it can be a very dry topic unless, as a philosopher, one immediately tries to say, well, this is the reason why it's relevant to study the history of this particular discipline. So I would like to start with that instead of jumping immediately to artificial intelligence, to try to give you a sense of why it's relevant, the debates and the two paradigms of artificial intelligence that I'm going to be discussing today. The paradigm based on symbols, symbolic artificial intelligence, and the paradigm based on causal connections, called the neural net or connectionist artificial intelligence. In my first book, I tried to bring out the relevance of artificial intelligence by linking it directly to warfare. Not that it is the only use of artificial intelligence, but it clearly, the Defense Department and DARPA, the Defense Advanced Research Projects Agency, have been one of the main funders of artificial intelligence since the 1950s. And for good reason. There is all kinds of applications in warfare of artificial intelligence. And so in that book, and I'm not going to go over that today, even though it clearly, with the war in Iraq and so on, it is an important topic. But I chose warfare because I wanted to study social spaces which were deeply material. And the battlefield is a social space. Animals don't have wars. Animals may have ritual aggressivity against one another, but they certainly do not have wars. And so the battlefield is a very social, deeply social space, but it is inhabited by bullets, by shock waves, by schnarpel, by wounds, by blood, by all kinds of things that are deeply material. Ideas are very important. Not only the ideas that go into tactics and strategy, but also the ideas, religious, nationalistic, and so on, that make people fight. But regardless of your beliefs and regardless of your linguistic categories, bullets will pierce your flesh. And that was my point of departure in that book, trying to study something social, but something in which the materiality of the social was not hidden behind the linguistic. Today I'm going to try to do a similar thing, but without going into too much gore and battle and warfare. Try to stay a little bit more on the peaceful side, but I still need to bring out this distinction that I'm very concerned about in my own philosophy. The two currents of artificial intelligence that I will discuss in a second, the symbolic school and the connectionist school, they are entirely different paradigms. The symbolic school, of course, is about symbols, mostly linguistic symbols, which are manipulated by rules, in some cases logical rules. And so it is a paradigm that we are very, very familiar with at least since Aristotle. Aristotle wrote the first piece of software, the first algorithm, the first mechanical recipe that was predicated on this paradigm. When Aristotle, for instance, demonstrated with his syllogism that if we say all humans are mortal and add I am human, then we can have a mechanical recipe that will derive from those two premises the conclusion, therefore I am mortal. Now that doesn't seem very exciting, and it is not very exciting because it only has two premises, but imagine the exact same argument with 22 or 25 premises. Your mind would not be able to cope with it, and yet Aristotle's syllogism as a mechanical recipe would go over the truth values of each one of those sentences and reach the correct conclusion. So, with a piece of software, with an algorithm as old as 2,500 years old, and an algorithm that retained its importance all the way to Kant and Hegel, both of whom discussed the syllogism as the state of the art in logic of their time. This is, of course, before Boole and before Bertrand Russell, before Frege invented all kinds of new forms of logic. Nevertheless, it retained its status as the first piece of software written, at least in the West, to manipulate symbols via logical rules, and it retains its importance for that reason. Symbolic artificial intelligence is, with modifications, based basically on that paradigm. You have symbols, in this case sentences, all humans are mortal, and then you have rules that apply to those sentences. In this case, rules to move truth or falsity from general sentences, all humans are mortal, to more particular sentences. Of course, deductive logic being, of course, the name of this particular software, is only one of the types of logic. A much more important and much more difficult to formalize is inductive logic. Inductive logic moves truth in the opposite direction. Instead of moving it down from the general to the particular, it moves it up from the particular to the general. This emerald is green. This other emerald is green. This third emerald is green. All emeralds are green. That is inductive logic. You go from many particular sentences and you generalize. Because you're creating and generating generalizations, inductive logic is, of course, much more akin to learning. Deductive logic is used by Sherlock Holmes, is used by people in mathematics doing axiomatics, and it has a very important use, and certainly in the foundations of mathematics is a very important piece of software. Nevertheless, inductive logic is the holy grail of artificial intelligence, because in order to teach a robot to learn from experience, you need to teach it inductive logic, how to move truth up from particular sentences to general sentences. To put it in very simple terms, nobody, to my knowledge, has devised a mechanical recipe that does this invariably across domains. Inductive logic remains the holy grail of artificial intelligence because no one has mechanized it yet. Mechanizing it would, in fact, imply having a model of learning in general. I'm going to give you some examples later on as to how symbolic artificial intelligence has tried to evade the problems with inductive logic and what aspects of it has been able to conquer. Nevertheless, that remains the main goal, or one of the main goals of symbolic artificial intelligence. Connectionist artificial intelligence is very, very different. It seems at first to be much more about animal intelligence. A connectionist a device in artificial intelligence is not programmed the way in which we programmed computers, the way in which we programmed symbolic devices. It is trained the way in which we train a dog to catch a frisbee. That is, you do it over and over, and then suddenly the neural network begins to acquire that capability. Not catching frisbees, I don't think that there's any neural network that does that, but to recognize patterns and to associate patterns one with the other. Pattern recognition is ubiquitous in animal intelligence. Even insects need to have pattern recognition. Think of, for instance, of the way in which bees navigate from the colony, from their home to the places where flowers and so on exist so that they can collect nectar and pollen. Well, they need to associate landmarks on the exit of on their way out, so they can then eventually recognize those patterns. They don't necessarily know there are mountains. They don't necessarily know there are tall trees. All they know is that there are certain patterns, and by associating those patterns and associating the patterns of petals and the odor patterns and even the sound patterns in some cases for some insects, they can act relatively intelligently without having any symbols in their heads. So the question was always, is that something that stops with animals, and the moment we become linguistic doesn't apply to us anymore? And this is where the questions about the two paradigms and how to make them pertinent come in. And before I continue with artificial intelligence, let me give you a sense of why this matters. Number one, and I'm going to apologize in advance here for stereotyping Eskimos, but I'm going to use a typical example because it is the one that was used throughout the 20th century to explain this dilemma. Everybody knows that Eskimos have at least 29 words for snow. Snow is very important for them, so they have 29 words for it. Automobiles are very important for us. We have many words for automobiles. Every culture that has a particularly important activity or a particularly important object will have many synonyms, many words for that particular object or referent. But the question is, Do Eskimos see 29 kinds of snow because they have 29 words for snow? That was the position taken by linguists in the 20th century. Words cut out experience and, in fact, give form to experience. Linguistic categories shape reality, at least phenomenological reality, and therefore their having of 29 words for snow is the reason why they can see 29 kinds of snow. That's one position. The other position will be the opposite. They have 29 words for snow because they can touch, feel, smell, build igloos with, and do all kinds of non-linguistic things with real snow, which comes in 29 kinds because there are 29 at least different mixtures of the solid and the liquid, and you're going to have different consistencies of snow, different types of snow combined with ice in different proportions. You're going to end up with an actual materiality which is rich enough, even in the case of just snow, that is in the case of solid water, to have 29 different combinations which can have 29 different uses and offer Eskimos 29 kinds of opportunities and risks that are real and objective, and that because of that they end up with 29 words for snow. Words for important things, as I just said, accumulate synonyms in order not to disappear for one's vocabulary, had to acquire subtle shades of meaning. And so starting with a few synonyms for snow, you can end up with 29 words for snow, which of course then play a very important cultural role in the transmission of knowledge about real snow. Nevertheless, the two options remain quite different. In one, the 29 words are shaping perceptual reality literally. In the other, perception is not linguistic. Perception is multimodal. It's about sounds, it's about smells, it's about textures, it's about images, all of which have their own modality and they can be combined in different ways. It's also about intervening causally in the world to build igloos with that snow, to hunt over that snow, to find your way out of a snowstorm. All kinds of things that are not linguistic, that imply that your body is situated in a situation in which the materiality of the situation matters and makes a difference, and because of that, you end up with 29 words for snow. So the two kinds of artificial intelligence that I was talking about at the beginning play a role in this discussion. If the symbolic paradigm turns out to be the correct one, then perhaps Eskimos see 29 kinds of snow because they have 29 words for snow. But if the connectionist paradigm turns out to be the right one, if a lot of what humans do is about pattern recognition, visual patterns, smell patterns, or odor patterns, sound patterns, textural patterns, then perhaps the second option is the correct one. They have 29 words for snow because they interact with their bodies with 29 kinds of snow. Now, that is a very important debate. I don't want to say that this is what it all boils down to. Let me give you, just before I move on with artificial intelligence, just one more example of why I think this is very important philosophically. The resolution of the first question, by the way, is extremely important philosophically. It can make you into a Kantian if you accept that the 29 words are what shapes reality, and of course a neo-Kantian, which was the official philosophy of the 20th century. Most phenomenologists, most philosophers, in fact, were neo-Kantian. If you believe that the signifier shapes reality, well, that's a neo-Kantian position. And the other position was relegated to almost nothing. Very few people actually were Humeans, seriously Humeans, in the 20th century. Scientists, perhaps, but scientists have a way of using positivism as a kind of public relations a maneuver where they don't really want to discuss philosophy, so they just, they say, well, we are just in the business of controlling and predicting, don't bother us with anything else. So philosophers really didn't embrace this until recently, the last 20 years, thanks to neural nets, thanks to the fact that we now have a technological paradigm of what it is to reason and to behave intelligently without any symbols whatsoever. For the first time, we philosophers have something to grab onto. The Symbolics had Aristotle's syllogism for 2,500 years. This is why they have a lot more of a tradition, a lot more of legitimacy. We Humeans had very little to grab onto until connectionism came along. But let me give you one more example to show you that this matters more than just some esoteric philosophical question about what comes first, words or sensations. There's a distinction that a British philosopher named Gilbert Ryle made in the 1940s when he was still alive between knowing that followed by a blank, which is always filled with a declarative sentence. Knowing that Columbus discovered America in 1492. Knowing that the Yankees won the World Series, when was it? 2002, whenever it was. In other words, is knowledge about symbols, is knowledge about sentences, is knowledge that is encapsulated in sentences that express, truly or falsely, facts. The sentences can be general, they can be particular, but nevertheless they are sentences. So Gilbert Wright called that know that, knowing that. And then he opposed it or contrasted it with knowing how to ride a bicycle, knowing how to swim, to take a couple of very humble practices, but also knowing how to design, knowing how to build a maquette, knowing how to create a sculpture. Knowing how is not taught by being told something or by reading a book. It's taught by doing. I mean, it's learned and taught by example. You have to engage in those practices. You have to form an assemblage with a bicycle, a piece of solid ground, and a gravitational field, all of which must be real. And then the kid has to actually find in his or her own body that point of speed at which the bicycle keeps itself up, but also know that when you have to slow down because there's traffic in front of you, you're going to have to exert more control over the bicycle because at lower speeds it needs more deliberate control to be kept up and at equilibrium. Very few parents give kids a book or a lecture and then throw them down the hill on a bicycle. Like, good luck to you. You actually, if you're going to teach them at all, you teach them by example. You jump on the bicycle and you see how it's done, see how I don't fall down. And then the kid has to do it. There's absolutely no other way. And it has to become an assemblage with the materiality of the bicycle, the gravitational field, and the piece of ground. Think of knowing how to swim. Again, you don't really tell your kid all these things about swimming, all the sentences, and then throw them in the deep side of the swimming pool, unless you are, of course, a sadistic parent. You have to, very little, make him or her, lose the fear of going into the water, and then by actually performing those rhythmic movements that keep you afloat and interacting with actual water, you eventually develop that piece of know-how that we call knowing how to swim. Now, I just used some relatively humble examples, but of course, know-how, expertise, is everywhere. I mean, students don't have to be told that when they show up for a new job after graduation and they say they cannot just list the books they read, they cannot just list the know that. The first thing that an employer is going to ask them is, well, do you have any experience? Have you actually done this? Do you have any know-how? So it is something that it is quite ubiquitous and confront us all the time. But also think about this. Knowing how to read, knowing how to write, two abilities that are crucial for a literate society, at least, with language has already have a written version, and which are forms of know-how that sustain language. So even if we need language to speak about skills, the way I'm doing it right now, we need skills to use language. So that distinction again goes back to the exact same point that I was talking about before. Knowing how to ride a bicycle, knowing how to swim are embedded, embodied knowledge. It's a very complex form of pattern recognition, since you know how to recognize patterns that your legs make with the pedals, that your body makes with the bicycle makes with the ground. So it's not just about visual patterns or auditory patterns, a much more complex form of sensory motor pattern completion and recognition, but nevertheless gives us the kinds of activities that, according to Gilbert Ryle, who coined the distinction, has been systematically neglected by philosophers. And perhaps there's a class aspect to all of this. Artisans, metallurgists, for instance, are all about know-how. Metallurgists have been with us since ancient times, and yet philosophers have always been suspicious of metallurgists. Metallurgists don't talk very much. In Greece, they wouldn't go to the agora to discuss friendship and patriotism. Well, if you don't come to the agora to discuss friendship and patriotism, you're probably not a very good patriot. And you're probably not a very good friend. And you're there by the fire, banging on metals all the time. So there was kind of a suspicion of a craftsman. And if not a suspicion, because Xenophon actually wrote it that way, applying the mechanical arts should be illegal even in the warlike countries. Of course, that was, the swords and everything made out of metal was being made by these people. It's just that they didn't understand. They didn't understand what it was. That was knowledge that was possessed by the metallurgist. It clearly was not verbal knowledge. It did not lend itself to philosophical speculation as easily as symbolic knowledge. So I introduced this just to give you a sense of where these discoveries will be impinging on. They will be impinging on our everyday lives, because our everyday lives are about know-how in large part, although, of course, symbolic knowledge will always have a role and will always play a role. So let's go back then to artificial intelligence. The two paradigms are exactly about that. Symbolic artificial intelligence is about trying to capture know that. It's about trying to capture, once you've learned a bunch of sentences, that, it has to be sentences in a declarative form, that is, sentences that state a fact, whether falsely or truly. What kinds of rules can you use to manipulate that truth value of that sentence? How can you pass the truth value from one sentence to another? How can you make that mechanical so that we can actually teach robots how to do that? We can just place a bunch of sentences in robots' heads, and then the robot would have enough logical rules to derive new sentences, new truths from those truths already there. I already gave you the example of the simplest form of this. All humans are mortal. I am human, therefore I am mortal. If a robot can do that, it is already performing symbolic logic. The simplest type of symbolic logic, but nevertheless it can do that. But of course, as I said at the beginning of the talk, the real challenge is how to go the other way around. How to start from a bunch of sentences that express particular truths. This Chihuahua dog is obnoxious. This Chihuahua dog is also obnoxious. This Chihuahua dog is very obnoxious. All Chihuahua dogs are obnoxious. How can we get a robot to come up with that conclusion? It's very, very different, because you're moving truth from the particular to the general, and truth doesn't move automatically that way. Artificial intelligence is, in fact, perhaps the very first artificial intelligence program. The origins are a little fuzzy, but the first big celebrated artificial intelligence program created by Herbert Simon when he was working for the RAND Corporation. Remember that RAND Corporation? An Air Force think tank. Think tanks emerged after World War II to kind of continue the relationship between science and the military into peacetime. The RAND Corporation was the first such think tank, basically staffed by mathematicians, linguists, and many formally oriented scientists. And Herbert Simon invented what is called a theorem prover. A theorem prover, just to repeat, just to get the terminology out of the way, when one really, really believes in deductive logic and really believes in symbolic intelligence, one of the paradigms of what a perfect system of thought would be is an axiomatic, such as Euclidean geometry. In Euclidean geometry, you start with 5 sentences that are self-evident, that is, whose truth is not in question and perhaps it is unquestionable. And from those 5 general sentences, using the little software that I just told you, how to bring truth down to particular sentences, one can derive a million other sentences called theorems from those 5 axioms. That form, of that royal form of the axiomatic, which of course is highly prestigious, Euclidean geometry was included by Kant together with Aristotelian syllogism, as one of the few forms of synthetic a priori, that is, things that are a priori and nevertheless were discovered in a non-analytic ways. They don't depend just on the meanings of words. In other words, what highly celebrated by Kant as one of the great achievements of humanity, and has remained a model of how to think, of what it is to create a system of thought that is truth, in this case a system of geometry that is demonstrably true. Well, when we operate in axiomatic, the deriving theorems from the axioms is very easy because truth flows spontaneously from the general to the particular. But trying to prove a theorem is a completely different thing. Trying to prove a theorem is a kind of inductive logic. You now have a particular truth that follows from the axioms, and what you now need to do is climb up the ladder, go in the opposite way, kind of swim upstream. Because now you have to prove that it follows from the axioms. You need to establish a derivation, a logical sequence that shows that this theorem belongs to the thing. It is as true. Its truth follows from the axioms deductively. So Herbert-Simon invented the first theorem prover, and at that point, everybody thought, bingo, we've got it. We have mechanized Aristotle. We have mechanized logic. From now on, and of course, many people falsely confused rationality or reasoning, at any rate, with reasoning deductively, which today we know is not true. Nevertheless, here he had managed to create a kind of inductive logic, and he went on to become very, very famous because, of course, to have a theorem prover that is completely mechanical and that a machine can do is already thinking inductively, even though it's thinking inductively within a very specific field, something that has been axiomatized. By the way, the mechanical recipes that I've been talking about are called algorithms. An algorithm is simply an infallible mechanical recipe, at least if it's a deterministic algorithm. Aristotle devised an algorithm for the syllogism. Then Herbert-Simon created an algorithm for proving theorems. By the 1960s, however, the artificial intelligence symbolic approach began having doubts as to whether this was extensible, as whether this could be extended to other fields that were not so clearly axiomatized, that had not been previously formalized. Because if the field has been previously formalized, robots excel in previously formalized fields because they are already been mechanized in a sense. They have already been made clean and everything, all the relationships are clear. So for a mechanical entity is the best of possible world. But how would robots perform with sentences in fussier fields like medicine or chemistry? Well, in the mid-60s, artificial intelligence researchers decided that algorithms are not the only way of doing this. They wanted to bring in that they call heuristics. Heuristics are basically just rules of thumb. They are recipes, just like algorithms are, procedures, series of steps that if one follows them, they achieve a certain result. But unlike an algorithm, a heuristic does not promise infallibility. So that's why it's a weaker form of procedure. Nevertheless, artificial intelligence researchers had to bite the bullet. They had to say, well, if we cannot have algorithms for inductive logic, let's at least have heuristics. But where do we get them? Well, heuristics are typically, because heuristics are recipes that do require knowledge, that do require judgment on the part of an expert, precisely because they are not infallible, and so you need to know whether they apply. I know this heuristic, this rule of thumb applied last week, but will it apply next week, or will it apply to this other case? They are basically domain specific. So what artificial intelligence did was to cheat a little bit. They began hiring experts, doctors, chemists, who were particularly good in one particular subfield. For instance, diagnosing certain types of diseases. To make a diagnosis is a kind of inductive logic, right? You start with a bunch of sentences like, the patient has a runny nose. That's a particular truth. The patient has headaches every morning. That's another particular truth. And from those particular truths, you need to go up into a general truth. The patient has a flu. The patient has this or that disease. Now you're classifying them under a general category. It's a kind of inductive logic. Yet, of course, doctors do that effortlessly. And they do it through heuristics. They don't have a theorem prover inside their heads because medicine has not been and will never be axiomatized, so you cannot have that kind of mechanical recipe. Nevertheless, if you could hire a doctor and then submit that doctor to an intense interrogation, force that doctor to articulate that know-how that he or she has developed over many decades of practice and experience, and many times it's unarticulated. Many times a doctor will just go, if those symptoms are present, then I will ask an extra question, and if that extra question is yes, then I know this is the disease, but they couldn't really tell you, this is the logic through which I actually did this, I just know how to do this. But in the room of a knowledge engineer, as these people were called, he had no choice, he or she, because it doesn't really matter for this. They had already told him or her that they were going to immortalize their ideas. You know, it's like, we're going to extract your know-how and we're going to put it into a symbolic artificial intelligence, and you're going to become famous because the soul of your thought is going to be here. So after they told that to the doctors were, okay, like, do whatever you want with me, you know. And so they were submitted to this rather strong form of interrogation with video cameras and so on, to try to force the doctor to articulate that know-how, to articulate that implicit knowledge. So presented with a series of symptoms, the doctor would give a possible diagnosis, and then they would try to say, well, but now think about the steps that you used to get to that diagnosis. And little by little, they force the doctor to articulate all that implicit knowledge. The knowledge engineer, who had designed not only the interrogation procedure, but also how to start now formalizing what the doctor was saying, would end up with a series of if-then rules, if-then being, of course, your basic logical operator. If all humans are mortal and I am human, then I am mortal. And a series of if-then rules with many exceptions and so on. This is called a knowledge base. And it was basically heuristics. Heuristics extracted from an actual doctor. The system that results from those heuristics in operation with an interface and a whole other components is called an expert system. Expert systems are perhaps the most significant success of the symbolic school of artificial intelligence. They actually work. They work in very specialized knowledge domains. They are more like idiot savants than geniuses, in the sense that they know a lot about this one particular subject, but then you ask them about something else and they are like, Nevertheless, you trust them. You trust them. There's the expert systems already working in hospitals. There's expert systems working in chemistry. In chemistry, for instance, what they needed to know is, if you look at several pictures of spectrograms of particular molecules, certain chemists, just from looking at the spectrograms and all the information, could tell you something about the molecule, the form of the molecule that was producing that spectrogram, and that was a type of inference. You were going from a certain type of data that gave you certain statements about the spectral properties of the radiation coming out of that molecule or bounced off that molecule, and you had to figure out the architecture of the molecule. Well, that turned out to be a lot of heuristics too, developed through know-how, but nevertheless that you could extract from the chemist. So a chemical expert system was also created in the 1960s and was quite successful. To this day, expert systems remains perhaps the most successful part of symbolic artificial intelligence. And so one has to give it credit. Nevertheless, one has the feeling that some cheating has been done here. One is using the actual human body of an expert to learn that know-how, to develop that knowledge from experience, and once that body with its nervous system and its practices and its interventions in reality and its having assessed opportunities and risks and having made mistakes, all that history of that doctor or that chemist, which is now invisible to us but is there recorded in his or her body, you're using that as a bridge to go into your expert system. But of course, what we would really want artificial intelligence to do is to do the doctor in the first place, or the chemist in the first place. That is, to learn by doing, to learn by experience, and to learn by example, just by looking at other experts performing their trade. This is where connectionism offers a promise. I'm going to start with the simplest examples. Connectionism is based, or at least inspired by the human brain. In the human brain, it's very hard to find any one particular piece in which there's a symbol here that's being manipulated by a rule that's over here. All we find is a bunch of populations of neurons connected to one another in different ways, exciting or inhibiting one another in waves, and by this causal interaction, inhibition and activation or excitation, they manage to compute. Not only do they manage to compute, they manage to create the virtual reality that I have in front of my eyes right now. I mean, brains are quite fantastic little machines. And yet we understand so little as to how inhibition and activation by themselves can produce something we would call computing, something that we would call reasoning. One way of thinking about it is, of course, thinking in terms of simple animals, and for instance, ants or termites. Ants and termites are able to produce quite amazing feats of engineering, or at least architecture. Termites build arches, for instance. Ant hills sometimes seem like a gigantic computer. They can compute, for instance, in scare quotes, the closest distance or the closest path to a particular piece of food, without having those instructions hardwired into their genetic endowment. They actually do it collectively, and they don't even communicate with one another. They communicate through the changes they make to the environment by putting a little bit of pheromone into the mud that they are now working on. That pheromone excites other ants, which begin adding more mud, or to other termites in that case. Lines, for instance, form simply by a scout randomly moving and bumping into a particular piece of food, having a little behavioral rule that says once you bump into food, get all excited, and then come back to the colony with some of that food, dropping a drop of pheromone as you go along. And another behavioral rule that says if you bump into a drop of pheromone, follow the trail either way. After many of those ants do that, then a trail forms reliably from one place to another without any central direction, without any symbolic interaction, without any representations. So the idea would be to think of the brain as ant hills, but of course many tribes of ants, the hippocampus, the cerebellum, all these different organs having their own tribes, their own collectivities of neurons, each one dedicated to a particular function. And the idea that ants and termites simply excite or inhibit one another, but nevertheless from those excitations and inhibitions something emerges, which is anthill intelligence, would be something that we could also very reliably apply to the brain. That is what neurons are doing to one another, what insects do to one another, at least social insects. So connectionism takes its inspiration from that. A connectionist device is simply a set of computing units that are extremely basic. All they can do really is, in other words, they are way more basic than the CPU inside our personal computers or any computer that we experience in our desktops. They are simple computing devices, but they always come in bunches, like ants do, and they have specific connections to one another, and they excite or inhibit one another. And by doing that, by transmitting waves of activation and waves of inhibition, they can actually learn patterns, associate patterns, create patterns. Let me give you some examples. The very first modern connectionist device, the very first neural-like devices were created in 1943 by McCulloch and Pitt. Those were binary neurons. I'm going to skip that part because no one really followed their work as intensely as they did later on. Rosenblatt's perceptron. A perceptron is a neural net which is capable of associating patterns. Remember that for Hume, learning was a lot about associating things. In Hume's philosophy, as opposed to, say, Kant, for whom words structure reality, for whom categories, general categories, literally structure reality, for Hume, reality was just a wild world of sensations. Odors, colors, sounds, textures. And what gives it coherence was habit, routine. More specifically, the habitual association of co-occurrent things. So if I'm a baby and I see the face of my mother and that nose always goes with those eyes, that it always co-occurs in space, that nose with those eyes, with those cheeks, with that hair, then I learn to recognize it not just as eyes, nose, hair, and cheek, but as the face of my mother. If I habitually see that co-occurrence in space of those features. Co-occurrences in time were also very important because that gives us cause and effect, at least in the case of linear causality. If every time I light up a match and put it next to a paper, the paper goes on fire, now I know that lit match co-occurring with paper is also going to co-occur with paper burning. Or if I hit a particular billiard ball and the billiard ball hits another billiard ball, I know that the event collision will typically be followed by the event change of motion of the balls that were involved in the collision. From those temporal co-occurrences, as well as from the spatial co-occurrences in the case of a face, by habitually seeing them, we, little by little, as babies and then as infants, we start giving a structure to reality entirely without symbols. It's just a matter of moving in reality, of touching reality, of a structuring reality with one's body in a way. So what connectionists did is give Hume finally a technological instantiation. The symbolics, of course, the symbolicists, had Aristotle on their side, they had Kant on their side, they had Bertrand Russell on their side, they had a long tradition of people who have thought that reasoning is all about language and about sentences and truth and meaning. Hume didn't really have that many people. And worse, when he did have followers, such as Skinner, the behaviorist, for whom everything was an association between stimulus and control, the behaviorists, the fact that the behaviorists were actually taken to task in the 1950s and 60s by people like Chomsky, that is, by the new cognitive paradigm, and the prestige of behaviorism completely died, at least within philosophical circles in the 1960s, given that Skinner was the only Humean that was kind of pursuing the paradigm, the fate of Hume seemed sealed by the 1960s. We were all going to go in the symbolic way. We were all going to go into Eskimo Sea, 29 kinds of snow, because they have 29 words for snow. And then something happened. Someone invented an actual piece of machinery that performs those associations. It was called the perceptron, and it was very simple. Imagine that you have a set of input units. This can be thought of as simply sensors, but computing sensors capable of therefore becoming activated or becoming inhibited, which are connected not to each other, there are no lateral connections, but connected to another layer called the output layer, which also has a bunch of computing elements connected to each one of the previous ones. And there's a simple rule which is called Hebb's rule, which also applies to the brain. The more two units that are connected fire together, the stronger their synapse or the connection becomes. The less often the units fire together, the less strong the connection becomes. This was encapsulated into a slogan: units that fire together, wire together. And it's a very simple thing, but it actually works. The way you would normally use a perceptron with those two layers is you would present it a pattern. You can think of it as a visual pattern through a TV screen, through a TV camera that gets now fed to the input layer. You can think of it as a microphone that's picking up sound patterns. You can think of it as a feed from the stock market in which the Dow Jones is sending information to those units. And then you would train the neural net by giving it the output pattern that it should associate with it. This is more like training an animal rather than programming a robot. You would then feed it the input. You would give it the output, the correct output. And, of course, now the units that were active together, their wires will become stronger. And the units that are not active together, their wirings or the connections will become weaker. Once you finish with the training, then you take out the output pattern and you present only the input pattern. But now, because the weights have changed, the input pattern now will produce the output pattern automatically. In other words, you excite the inputs, and they will send excitation through all the connections, but some of the connections will be transmitting more excitation than others, and will excite some of the output units, and the output units will reproduce the pattern that you train the unit with. Now, this is not very exciting, but it is something that could be used to model, for instance, bee behavior or ant behavior. Ants and bees also perceive patterns in simple terms like that. They associate multi-petal shapes, for instance, with flowers, without having the concept of a flower. They associate gradients of color, accumulations of a particular wavelength, a particular frequency, which is the color of a field of flowers, with the nectar that they are supposed to be looking for. They can also associate landmarks with their beehive in certain positions, and even the direction of the sun as a pattern with other patterns. So by matching pattern to pattern, they can actually recognize things. In the case of the neural net, one says that once the training has been finished and the output pattern has been withdrawn, when we feed it the input pattern, if it produces the output pattern, we say that it has recognized the pattern, although no act of aha actually occurs, because we're talking about an insect here. The perceptron became instantly famous and then became instantly infamous. The symbolic school struck back. Marvin Minsky and Papert, one of his partners at MIT, wrote a book called The Perceptron, in which I'm not going to say they lied. They certainly were competing for funds. They were competing for funds from DARPA. They were competing for funds from other government agencies that it was only a certain amount of money for artificial intelligence, that they were competing for funds. So that must have been part of their motivation, but I don't want to make this into a see-me political thing. The fact of the matter is that the Perceptron book completely canceled research on connectionism for about 15 years. It correctly noticed the problems with a two-layer perceptron. It couldn't do many things that humans can very easily do. It was good for insects, but you could not scale it up. You could not move from that to, say, chimpanzee intelligence and then human intelligence. It was very narrow in its application. So the book, The Perceptron by Minsky and Papert, closed the chapter on that part of connectionism and dried up all the funds to connectionism for about 15 years. Even though people already knew at the time that if you added more layers between the input and the output layers, all these internal states, you could go way beyond the problems that the initial perceptron had. Multi-layer perceptrons then begin to appear in the 1980s, thanks to the work of people like Rumelhart and McClelland. They call it, not connectionism at the time, but parallel distributed processing, the PDP approach. Because, of course, all those units act in parallel, and they are distributed. There's not a central computing unit, a CPU, a central processing unit, like there is in our computers. And so it's distributed, and they do process information. Now, whereas the perceptron was a strictly Humean machine, it was creating associations between patterns, just like Hume said. You associate contiguity in space or continuity in time with certain patterns. Multi-layer perceptrons go beyond that because the intermediate layers, also being just basically simple computing units connected to the others, these layers are called the hidden layers because they are neither the input, they are neither the sensory input nor the motor output, but the kind of internal states of the neural net. Those hidden units turned out to be quite amazing, particularly if you interconnected them correctly. In particular, they were able to derive what is called now distributed representations from the input. In other words, unlike the first perceptron where you had to give it the actual output, so it would make the connections, and in a way you're cheating by giving it the final solution instead of letting it learn, this new multi-layer perceptrons and all the new varieties, recurrent neural networks and so on that are coming out the pipeline, were actually able to extract their own micro-features from the inputs that they were exposed to. This is particularly crucial in the case, for instance, of face recognition. Face recognition is another one of those holy grails of artificial intelligence, when you move from sentences and logic to visual images. And of course, in post 9/11 world. It's become a major industry. And symbolic artificial intelligence has a very hard time recognizing faces, because you can give it representations, say photographs of a face in different angles, but you cannot give it all the different lighting conditions. You cannot give it all the different slightly weird angles. You cannot, gestures in the face, add a mustache, And they are not particularly good at generalizing from their database. They can recognize a face if it fits their representations that they have, but they cannot really go beyond that. Multi-layer perceptrons in different configurations can actually be quite good face recognizers. And what they do is, not only do they have patterns at the input and the output, as I just said, but they create their own patterns, which researchers typically are puzzled about. They have to go in there and investigate what's going on. These are called distributed representations, which are the neural network's own representation of the data. They extract microfeatures, which when you actually go in there in the hidden units and find out what's going on, you realize, how did it pick up that a piece of nostril with like a piece of earlobe was a relevant feature of a face? I would have never imagined that, but they extract their own relationships from these co-occurrences of features in a face. And then they decide entirely on their own what is going to be the pertinent and significant ways of associating all those features so as to be able to recognize that face from all kinds of different angles, from all kinds of different lighting conditions. In other words, multi-layer perceptrons not only can associate patterns, they can complete patterns. If you train them with a particular face, and then you just give it part of that face, as long as enough of the face is showing, which would be a typical case in a surveillance camera, of course, because you would now see a face from here, or there would be a tree in front of the face, or something that would be kind of hiding part of the input. Multi-layer perceptrons can now complete the pattern via their own internally generated representations. These are not symbolic representations, however, they are dynamic representations, because the only thing that is stored in the neural net is the pattern of the weights or strengths of the connections. Every time, and so there's no real representations stored there, but every time one activates its input layer with some stimulation, it, through the weights of the patterns, it recreates that representation. So today, for instance, this ability of distributed representations to be content addressable, let me just explain what that means. In your typical symbolic computer, things are stored in your hard disk, things are stored in your memory, and in order to retrieve an item, in order to retrieve a file, in order to retrieve an image, that you have stored you need to have a certain address. Everything has an address, whether in RAM, in the memory for the display and the real-time behavior of the computer, or in the hard disk itself. But everything must have an address, and everything you can retrieve that memory by checking its address. But of course, the brain doesn't have a system of addresses. We don't have, like, neuron number 5 connected to number 6. That's where this memory is. Memories are retrievable in our mind by content. We live a particular experience, which may have, say, the smell of wood burning, and then it was a misty night, and you saw some lights of the house that you were looking for, and you finally found it. And then years later, you have that same smell, and pow, the house, the mist, the lights, all come back together. You can address the memories, or if you want to put it this way, you can retrieve the memories by their content, and by quite tiny little parts of their content. Sometimes it is a song that reminds you of the first time you heard the song, or reminds you of a particular situation where you last heard that song. Sometimes it's a smell, sometimes it can be a color, sometimes it can be a word. But it's always part of an assemblage of sensations. And once you are stimulated by one of the components of that assemblage, the entire assemblage comes back to us. This is the mystery of memory, of episodic or autobiographical memory, not memory of facts. I remember that Columbus discovered America in 1492. That's another type of memory. That's semantic memory. That's very important too. But today we know that amnesiacs, or people who suffer certain kinds of amnesia anyway, can in fact completely lose their semantic memory, not remember any facts like that, but retain autobiographical memory, or vice versa. Certain types of amnesia will completely leave your semantic memory intact, so you can repeat facts verbatim, just as you were before you had that disease or that accident that impacted your brain, but you cannot remember the situations where you actually lived or learned those truths. So today we know by dissociation experiments that the two types of memory are different. We know that chimpanzees and birds, for instance, pigeons in particular, have episodic memory. You can test them with photographs and operant condition or instrumental conditioning setups so that, you know, only if they see certain patterns and remember that they have been there, they can get the little food pellets. So we know that episodic memory, that is content addressable, is much more primitive than semantic memory, which you need language in order to have. So what neural nets, multi-layer perceptrons with the concept of a distributed representation, that is a representation that is not stored. All that is stored is the weights of the connections. The representation is recreated every time you remember it, which is exactly what our memories are. You recreate them with that smell, with that sound, all the sun, the whole thing gets reproduced vividly in your mind, have given us a way of finally tackling the question of what kinds of intelligence we inherited from our past as primates, from our past as biological entities, from our material bodies, and what kinds of memory are strictly about symbolic representations and propositions, truth or false propositions. I'm running out of time, so let me try to conclude this. There's many other, one of the interesting things about neural nets is that every time one of the symbolic school people write a book against them, all the neural net people have to do is come up with new designs. In other words, the argument doesn't end in a logical way. The perceptron was limited, yes, and Minsky and Papert wrote a very good book saying why it's limited. But all that was needed is to add more layers. Well, now multi-layer perceptrons are limited. For instance, they cannot remember things in time. And remember that Hume was not only about co-occurrences in space, but co-occurrences in time. Well, now we know that recurrent neural nets, where there's feedback between the output and the hidden layers, or between the hidden layers and the input layers, so the connections go not only in one way, but in the other way, can, in fact, learn about coexistences, or co-occurrences, rather, in time. Every time a member of the symbolic school declares neural nets, well, this is as far as they went, and they will never go any farther, and therefore let's all go back to sentences. The connection is all they have to do is come up with a new design. So what I find fantastic about this is precisely the open-endedness aspect of the project, the fact that it is a cauldron of creativity, the fact that the limits are really the limits of the imagination of the designers of neural nets. And therefore, it's not going to be the kind of argument that can be settled by logic alone. It has to be settled by getting your hands into reality, interconnecting those units, creating new designs, training them, testing them, and see what they can do. In other words, it's going to be a lot about know-how, knowing how to design new neural nets. So know-how, at the level of the body, is now beginning to interact with the first technological objects that actually can learn know-how, that can learn from experience. And from that interaction, Hume will be recovered, and Hume will be, in fact, validated. Now, as I tell my students, unless you are a very strict conceptual artist who all that he or she wants to do is things with words, if you are just about any other kind of artist, a musician, a choreographer, a painter, someone who deals with colors, with sounds, with intensities, you are much better off with a theory of perception, a theory of experience that's Humean, because Hume is all about those intensities. And even your subjectivity, when you are in the process of creating a new work of art, and you feel like you lose yourself in the work of art, well, that's also very Humean, because Hume says your subject, your ego, your person, your more or less stable personality, is something that emerges through habit. It's a kind of crystallization in a world of sensations, not only external sensations, but internal sensations, feelings of pride and humiliation, feelings of hatred and love, feelings of sadness and joy. And our psychic agency, is simply a crystallization in a field of perceptions that is not ours. And the way you can tell that is when you go into a delirium, cabin fever, or even a fever of 105 degrees. I mean, that's one of the things that I love about this, is just how easy it is to get rid of the subject. You know, just turn on the button, the fever button a little bit, 105, 106, and you're in a delirium. And when you're in a delirium, you now are fuzzy. I don't know who I am anymore, but your sensations are there. Only now they are forming a wild delirium. There's so many ways of triggering that state, sensory isolation chambers, even an excess of alcohol, that it gives us a sense of how our sensations are not really ours. We as a psychic entity, we're inhabiting a body that has its own life, and the sensations, and both internal and external, have a life of their own. We tend to think that they're ours because, via habit and routine, we have given them a certain territoriality. We have made it ours. But then when we begin to dissolve via a variety of methods, we begin to rediscover how the sensations have a life of their own, and how, as artists, we may owe them something. How, as artists, it may be not the right thing for us to do to try to slave all those sensations to language, to words, and affirm that it is the words that give them sense and coherence, but rather to give them their own autonomy, their own independence, even if we use them to our own benefit. So, to conclude this talk, whereas Hume did not have a paradigm that was robust enough throughout the 20th century to make it into a viable option for artists and for thinkers, and therefore the 20th century was mostly neo-Kantian. Today, towards the end of the 20th century, the beginning of the 21st, we finally have found that paradigm. It doesn't mean that language is going to become irrelevant. Language is clearly very important, but it's going to be cut down to size. And we need to, right now, rethink the role of intensities, visual, auditory, the smell intensities, texture intensities, in our lives and in our art. Thank you very much.